Hi guys, John the Quant here. This is week 4 of the data science bootcamp that I am providing here and also guiding in person at the Community College of Aurora. Now, if you did not start in week 1, there's going to be a pop-up over here maybe or over here, and I highly recommend that you do start there and go through everything because the weeks build off of one another. Like last week, we talked about how to transform data to make it more symmetrical and how to scale it to have it be centered over 0 and have a spread of like 1, standard deviation of 1. And we talked about why you want to do that. And this week, we're going to see even more why you want to do that because we're doing linear regression. This will be our first machine learning model, our first time actually making predictions using the computer. And linear regression is seen as pretty simple and it's seen as not very powerful, but it is very important, perhaps the most important model because it allows us to do hypothesis testing. So what we're about to do now when we go over to the computer is we're going to learn about hypothesis testing. We're going to do some hypothesis testing, check it all and make sure that it works, and then you'll use a linear regression model to predict whether or not somebody has diabetes. So let's get into it.
All right, let's get down to some linear regression. First, we have our imports, and most of these are the same: pandas, numpy, matplotlib, pyplot, and of course cboy. Now, I ended up using these actually. So for this one, first we're going to talk about two different kinds of linear regression. The first one is called OLS, or ordinary least squares regression, and that is in the statsmodels.api package. So I'm just importing that statsmodels.api as in. We're also going to do logistic regression, and we'll import that from statsmodels as well, but we're going to import that later. Now here I'm loading both the original diabetes data that we've been working with this whole time, and also the transformed data from last week. So this transformed diabetes data has been it's been gone through, and we've transformed all of the features to make them, like you can see down here, they've all been transformed to make them symmetrical or as symmetrical as possible, and scaled to have mean 0 and standard deviation equal to 1. And then we've got the 2 buckets that we made as well. So before we start doing hypothesis testing, which is something we're going to do on both of these actually, we'll talk a little bit about what research is. Okay, so research really just means finding the answer to a question. And that's what data science is really about, and it's what all of research is really about. I mean, remember, like back in week 1 in that first video, we said that data scientists create value by generating information, and that means that data scientists are doing research. Okay, we're finding answers to questions. And there are a lot of ways to answer questions or to generate new information, but in this boot camp we're going to focus on a very basic form of quantitative research, which is hypothesis testing with linear regression. Now this is probably the most common form of quantitative research. I mean, it shows up all the time, and once you learn how to interpret it, you will recognize it all over the place. It's going to be everywhere. So just a second ago we said that research means finding the answer to a question, so we need a question. All right, that's going to be our research question. There are a few things we want to keep in mind when formulating research questions. And the first one is that your research question must be objective. You can't use words like better. Okay, so here's an example. A bad example would be, is lower BMI better for health? Well, you can't say better, okay? That's not objective. What you can say is, does having a lower BMI decrease the probability of being diagnosed with diabetes? All right, really think about all the words that I'm saying there. Does having a lower BMI decrease the probability of being diagnosed with diabetes? All right, several important things here are being diagnosed with diabetes. I didn't say having diabetes, I said being diagnosed. Because if you think about it, that's what our data really is. We don't actually know if these people have diabetes, but we do know that they were diagnosed with diabetes. And I didn't say anything about better. Like, maybe for whatever reason, maybe we want diabetes. Maybe having a lower BMI is worse in some other way. So we can't say better. We can't say worse, but what we can say is, like, what is the actual, literal, objective effect that BMI has on the probability of being diagnosed with diabetes. So number one, it's got to be objective. Number two, it has to be specific, and you got to be really careful in choosing your words. So here's an example of a bad research question. Are fatter people more likely to have diabetes? Well, that's not specific enough, okay? What does fatter mean? What does more likely mean, right? So a better research question there would be, is higher BMI statistically associated with a higher probability of being diagnosed with diabetes? Again, really notice the words that I'm using. I'm not saying more likely to have, I'm saying higher probability of being diagnosed. And I'm not saying fatter people, I'm saying higher BMI. Because fatter and higher BMI might sound the same to us, but they mean something different when you actually measure them. Which leads us to our third characteristic of a good research question, is that it has to be measurable. All right, if you cannot measure it, then you cannot research it. So here's an example of a bad research question. How many people have diabetes? Well, let's make that better. Here's a good one. What proportion of the population is diagnosed with diabetes? Okay, now this example is especially tough because in common language, the two sentences, how many people have diabetes and what proportion of the population is diagnosed with diabetes, like they kind of sound like they mean exactly the same thing. But we have to recognize that we don't actually know how many people have diabetes. We only know how many people are diagnosed with diabetes. So we have to assume that there are a lot of people out there who have diabetes but go undiagnosed. So we can really never answer the first question. We can never know how many people have diabetes, but we can answer the second question, what proportion of the population is diagnosed with diabetes? And there are other important things to keep in mind when forming research questions, but to my mind, the rest of them are fairly intuitive. I mean, as an example, your research question has to be relevant, and I think, personally, that it's really just common sense that your question needs to be applicable to the problem you're trying to solve, right? All right, now that we've got a question, we have to form hypotheses. Now, you might remember learning about hypotheses in like middle school science or something, and it's the same general idea, but here, our hypotheses have to take a specific form, and we have to have two hypotheses. The first one, which we're going to call the null hypothesis, is the hypothesis that you're actually going to test, okay? And the second one is called the alternative hypothesis, and it must be true if the null hypothesis is false. So let's explain how we write those hypotheses, and that should explain what they mean too. So for this example, we're going to assume that our research question is rather simple, okay? Does BMI have a statistically significant effect on the probability of being diagnosed with diabetes? First, recognize that my research question fulfills all of the things above. It's objective, it's specific, and it is measurable. Okay, now we're going to make some hypotheses. So first, the null hypothesis. Now, when I am personally writing hypotheses, I try to think of the null hypothesis as the thing you would like to prove wrong. Now, people who teach this stuff at like university are probably ripping their hair out of their head when I say that, but I do find that simplification helpful, and so long as you understand the rest of what we're about to say, it's not a harmful simplification. It doesn't always work, but when it does, it can make writing hypotheses like really easy. So I want you to think of the null hypothesis as the thing you'd like to prove wrong. Okay, so for our example research question, which is, does BMI have a significant effect on the probability of being diagnosed with diabetes? The sentence I would like to prove wrong is, BMI has no effect on the probability of being diagnosed with diabetes. So that's our null hypothesis, okay? Our null hypothesis is going to be that BMI has no effect on the probability of being diagnosed with diabetes. When performing a hypothesis test, what you do is you assume that the null hypothesis is true, and then you find the probability of getting your data if the null hypothesis is true. So if it would be really unlikely to get the data that you've got when your null hypothesis is true, then that's evidence that your null hypothesis may not be true. And notice how carefully I'm choosing my words here. Okay, we can never really prove that the null hypothesis isn't true, but we can find evidence that it probably isn't true. When we find that evidence, okay, the probability of getting our data set is really low, then we say that we reject the null hypothesis. Now that's a bit of like statistician lingo, but what it means is that we have found evidence that the null hypothesis is unlikely to be true. There's the null hypothesis. The alternative hypothesis is whatever must be true if the null hypothesis is false. Okay, it must be true if the null hypothesis is false. So let's look at our example null hypothesis, which once again is that BMI has no effect on the probability of being diagnosed with diabetes. So if this is false, then what must be true? So if this sentence here is false, then BMI must have some effect on the probability of being diagnosed with diabetes. Okay, so either BMI has no effect or it has some effect. Okay, either it has an effect or it doesn't. If the null hypothesis is false, then the alternative hypothesis must be true. Now, the alternative hypothesis plays absolutely no role in the statistical test itself, but if we find evidence that the null hypothesis may be false, then we have found evidence that the alternative hypothesis may be true. Again, we can never completely prove that it is true. We can only find evidence. So in mathematical lingo, or mathematical notation, this is what our two hypotheses that we just formed might look like, okay? H naught, this is the null hypothesis, says that the effect of BMI is 0. And H1, this is the alternative hypothesis, says that the effect of BMI is not equal to 0. And that's it. This is what we're going to test. Before we get around to testing, let's talk about what linear regression really is, okay? So linear regression is a model that just multiplies each column by a coefficient and then adds it up. And you have seen linear equations before, and they look like this. Y equals mx plus b. Recognize that from like algebra 1, okay? Now that's a linear model with only one column, x, and one coefficient, m, and a constant intercept, b. So if we were to have 4 columns, it'll look like this. We have y equals a1x1 plus a2x2 plus a3x3 plus a4x4. Okay, so we have 4 columns. That's x1, x2, x3, x4. And we have 4 coefficients. That's a1, a2, a3, a4. And we have one intercept, which is b. Now you can only ever have one intercept, and sometimes that intercept is 0. The trick to linear regression is figuring out what the coefficients should be. All right, the computer's going to do that for us, but if you want to see how it's done, I made a full, super fast course on linear regression that goes through all the math and a whole lot of detail on how to use linear regression. There should be a pop-up on screen now. I think it's about 3 hours long, but it goes through all of the math underlying it, underlying linear regression, and it shows you a few ways to use it, especially in the world of finance and like portfolio management. So the important thing for us to know here in this boot camp is that if a coefficient is 0, then that column has no effect on the outcome. Okay, if you multiply by 0, then that's just 0. And if you add 0, then you haven't added anything. So if a coefficient is 0, then that column has no effect on the outcome. And the vast majority of the time, your null hypothesis will translate to the coefficient is 0, and the alternative will translate to the coefficient is not 0, which is exactly what we have up here, okay? This says our null hypothesis is that the coefficient of the BMI column is going to be 0, and our alternative hypothesis is that the coefficient of the BMI column is not equal to 0. And most of the time, this is going to end up being what your null hypothesis really mean. All right, let's perform a hypothesis test. Well, first you want your data to be symmetrical and you want it to be scaled. However, we're going to perform this test both the bad way, using just the raw diabetes data, and also the good way, using the transformed and scaled data. And we're doing this to show that the transformation and scaling matters. All right, so this is the bad test. It is bad, it's bad, it's bad, it's bad. Do not use the raw data like this. It is bad. But first, we need to split our data into features and target. Okay, so our features is the diabetes data without the outcome column, because that's our target column. And then our target here is just the outcome column of the diabetes data set. So all we've done is split those into two things. Okay, X is all of the columns except for outcome, and Y is just the outcome column. Now this right here is sm.addConstant. That's the add constant function from the stats models API. That it just puts a 1 on the end. Let's see, did I put it somewhere? No, I did not. Oh yeah, yes, I did. There it is. All right, so you see this? extra column here, constant, and it's just ones. That just adds this column of all ones onto the data set so that we can have an intercept B. If you don't do this, add constant before fitting a model, then you're assuming that B is 0. And we don't want that, so we put it on here. And then we have linear regression equals sm.ols of y comma x. And then to actually fit that, you have to do linear underscore regression dot fit. So you're making the linear regression by taking this object, giving it y and x, and then saving it to this variable, which I called linear underscore regression. And then you're taking that object and calling dot fit on it and saving that as a result. So now when we look at the results, that's result.summary. It's going to give us this whole table. And it's got a ton of information in here. And it's all good information. And if you're really interested in this kind of scientific hypothesis testing, then you should learn about this. And there's a link down below that to more information about everything that's in here. But in this bootcamp, the things that we're really going to look at least right now, are the coefficient column and this one, p greater than t. So this p column, all right, this tells us whether or not the column was statistically significant. Okay, so this answers our hypothesis question. So if this number is really low, really close to 0, then that means that it is unlikely that the null hypothesis is true. So here, our null hypothesis was that BMI's coefficient would be 0. So here we see that it's a little bit away from 0, but the important part is that it's far enough away from 0 that the probability of it being 0 is 0. That's what this tells us. The probability of this coefficient being 0 is 0. So since the probability of this coefficient being 0 is really low, then we can reject the null hypothesis, which just means that we found evidence that the null hypothesis may not be true. And it means we have found evidence that the alternative hypothesis may be true. So we found evidence here that BMI might have some effect on diabetes. But again, we're doing this the bad way. And you can tell it's bad by, like, look how tiny these coefficients are. Okay, skin thickness has a coefficient of 0.0002. All right, or what's another one? Age here, right? 0.0026. Tiny little coefficients, and that's because these numbers are like all over the place. Age ranged from, what did it range from? 20 to like 80. All right, so it's going to have a really weird coefficient. This is why you want to scale everything, is because when you scale it, then all of these coefficients are going to be comparable to one another. Right now, they're definitely not. All right, so how do you know if the number in this column is low enough that you can reject the null hypothesis? Well, typically what you do is you just pick some number. Okay, you just pick a number, and if it's lower than that number, then that's good enough. So the lower number you pick, the more certain you can be. So probably the most common is 0.05. So if we use 0.05, then this one, and again I'll remind you, this is the bad version. So if we use 0.05, then the constant would be significant, and pregnancies would be significant, and glucose would be significant, and blood pressure would be significant, and BMI would be significant, and diabetes pedigree function would be significant, because all of these have these p-values in this column, all right, lower than 0.05. So we would be able to say then that each of these ones with a p-value less than 0.05 has an effect on the probability of being diagnosed with diabetes. But again, this is the bad version, so don't read too much into this. Let's do the same thing, good version, okay? Same exact thing, split it up. We the x values, okay, the independent features, whatever you want to call it, that's now the transformed data without the outcome column, and y, what we're trying to predict, is just the outcome column. We add the constant, you can see that down here in this column. Do the same thing again, sm.ols of y and x, and linear regression.fit. And now look at these. Now this is different, right? Before, we saw that pregnancies was significant at a very low p-value, but now it doesn't anymore. And remember, all we've done here is scaled the data and transformed it to make it more symmetrical, and it shows a very different picture. So this is why you always want to transform and scale your data before fitting a linear regression to it. So here, what was significant? Well, we've got the constant, all right, the intercept b, which is like 0.27. Glucose, okay, that had a really low p-value, and its coefficient was 0.19. So it's a little hard to interpret after the transformation and scaling, but because this coefficient is positive, we know that when your glucose level goes up, that makes you more likely to be diagnosed with diabetes. So a higher glucose, more likely to be diagnosed with diabetes. Let's see, blood pressure, not significant. Skin thickness, not significant. Insulin, not significant. BMI, still significant. And it's positive as well. So BMI does have some effect, or we have found evidence that BMI has some effect on the probability of being diagnosed with diabetes, which was our actual hypothesis up above. So we can reject the null hypothesis here, okay, and we have found evidence of the alternative hypothesis. So we have found evidence that BMI has some effect on the probability of being diagnosed with diabetes. And what effect is that? Well, again, it's hard to say exactly, but this is positive, so higher BMI. We have found evidence that higher BMI increases your probability of being diagnosed with diabetes, okay? Positive, so that means when BMI is higher, the probability of being diagnosed with diabetes is higher. Next one, significant here, diabetes pedigree function. Again, it's positive, so the higher your... So we have found evidence that if you have a higher diabetes pedigree function, then you are more likely to be diagnosed with diabetes. Age was not significant. Then we found that people in their 30s or in their 40s, both of these were statistically significant. And they have, again, positive coefficients. So basically what this means is that this is showing that as you get older, you are more likely to be diagnosed with diabetes. Because remember, if you don't fall into either of these categories, then that means you're less than 30 years old. So these coefficients, or this constant actually, are talking about a comparison between people in their 30s and people that are younger than 30. And this one, this is comparing people that are 40 or older with people that are younger than 30. I mean, yeah, younger than 30. That's the comparison that's going on there. So our regular person, the one that this constant is defining, is somebody who is in their 20s. So this means that people in their 30s are more likely to have diabetes than people in their 20s, and people that are 40 or older are more likely to have diabetes than people in their 20s. Now, before we really take all this to heart, there are some assumptions, okay, for hypothesis tests that we have to deal with. And interestingly, it's a lot easier to check these assumptions afterward than before, which is why we did it in this order. So normally what you would do is you would transform everything and scale it, and then you would fit your regression, and then you would check your assumptions, and whether your assumptions hold, that determines whether or not you can trust the information in this table. And we've got 3 assumptions that we're going to deal with. There are more, but we're going to deal with 3. First, the data is normally distributed. Okay, so that's that bell curve that we saw in week 2, all right? And it's the whole theoretical underpinning of hypothesis testing with linear regression is that the underlying data follows a normal distribution. So when we transformed the data to make it symmetrical, that really helped with this assumption. The second assumption that we're going to worry about is that the data is homoscedastic, and this means that the variance of each column is the same. So when we scaled all of the data to make its variance 1, that's going to really help with this one. And the last one that we're worried about is that the features are independent. Okay, and this means that the correlation between all of the columns of X is 0. Now, we didn't do anything for this in our transformations, but if you did last week's mini project and you figured out how to do principal component analysis, then you found one way to remove all of the correlation. However, PCA does make it a lot harder to interpret, so there's really no free lunch here. And there are a few other ways to deal with correlation in the features, but nothing that we're really going to talk about. So let's go ahead and check our assumptions that we have. The first one is normality, and we check for normality in the residuals rather than the original data. Now, residuals are the errors in the training data, the difference between the prediction and the true value. And the easiest way to check for normality is with QQ plots, which stats models make super easy. So from statsmodels.graphics.gof plots, I am importing QQ plot. And then I'm doing a QQ plot. This is the results from our ordinary least squares regression above. It's saved as results.resid. Okay, and then I'm just kind of pushing the QQ plot into the right place by centering it at the mean and telling it what its standard deviation ought to be. And then we're drawing a 45-degree line. So that's that red line there. And what we're really looking for in this plot is how close are the blue dots to the red line. And you can see that they're pretty close to the red line, which is great. This means that our assumption of normality holds. All right, because the dots for these residuals are close to that red line, the assumption of normality is not violated by our data. The next one is homoscedasticity, and that means that the variance or spread of the residuals is constant. Okay, we're going to check that with residuals as well, and I usually just use a scatter plot, so I've made a scatter plot here. That just has all of the residuals on it, and what we're looking for is that they should look kind of like a cylinder or like a rectangle centered around 0, and they pretty much do. There's like a couple of spots where they get a little bit outside of the rectangle, but it's really close between like -1 and +1. So it's a pretty good bet that the assumption of homoscedasticity is going to hold for this data set. The last one is independence of features, which I think is easiest to look at by doing a heat map of the correlation. So I've used Seaborn here to make a heat map of the correlation. I have it annotated, and I don't like the color map that it originally uses, which is like white and black and red. I find it very jarring. I prefer the yellow, green, blue version, which looks like this. And as you can see, like age and pregnancies is really highly correlated. Insulin and glucose is really highly correlated. Skin thickness and BMI is really highly correlated. So if we really want to be able to trust the coefficients in our results, our summary table here, then we couldn't use these columns that have these really high correlation, because that just kind of messes everything up. So if we really wanted to draw good inference and have like scientifically valid results, then we would need to take some measure to eliminate that correlation. And we could use PCA, although as we said, that makes the results hard to interpret. Or we could just like drop some features, maybe just get rid of the age feature or something, since we have these other buckets. Or we could maybe engineer a new feature that contains the same information but like eliminates the correlation. Maybe some like age and pregnancies are correlated, so maybe there's some kind of combination of the two that we can use. Get rid of both of those columns and just use the combination, and that way we still have all of the information, but we've removed the correlation between our features. And that it is most problematic when correlation applies to a feature you're specifically interested in, such as here between skin thickness and BMI. And in that case, well, you really need to remove the correlation for anything that the test says to be valid. All right. So if we really wanted to know exactly what is the relationship between BMI and the probability of being diagnosed with diabetes, we would have to deal with this correlation with skin thickness. But for now, we're really just not going to worry about it. So one other thing I want to talk about that has to do with hypothesis tests, okay? And that is confounders and colliders. So these are features or columns that are related to your target variable in different, like, problematic ways. A confounder is anything that you think might, I'm going to use the word cause, but don't read too much into that. I don't mean literally cause. Okay, that you think might cause both your outcome and one of the other features. All right, so like pretend that a person's skin color affects both their skin thickness and the probability of being diagnosed with diabetes. All right, some diseases are more prevalent by race, although I'm not sure if diabetes is one. So notice that we don't have a column for a person's skin color. So if diabetes and skin thickness are both affected by race, then our test would find a significant relationship between diabetes and skin thickness, even if it shouldn't. All right, so what we see here is that skin thickness and diabetes are related, but what is really happening is that skin thickness and diabetes are both related to skin color. We just don't see skin color. So we don't see the middle, we only see the ends here. So to fix this, you can include confounders in your features. All right, so once we think, hey, maybe race matters here, our results might not be accurate if we don't include race. We don't have to include it, but we need to recognize that our results might be off if we don't. Now, colliders, I had never heard the term colliders before reading a book. It's called Data Science, The Hard Parts by Daniel Vaughan. I like the term colliders. I think it helps understand more than other terms that I've heard. So a collider it's kind of the opposite, right, of a confounder. So if our outcome and one of our features both cause a different feature, then our linear regression might yield incorrect results. So, for example, let's say that having diabetes makes a person gain weight, and having multiple pregnancies also make a person gain weight. Okay, then BMI would be a collider. So while confounders can cause problems when they're left out of your features, colliders cause problems when they are left in. They can be really hard to find, they can be hard to diagnose, they can be hard to remove, and we're not going to detail identifying and removing colliders in this bootcamp, but you need to know what they are, and you need to just be aware that they might exist, and that if you leave them in, it can cause a problem. Here, though, in this bootcamp, we're just going to assume that there are no confounders, or there are no colliders that need to be removed, although we almost certainly do have two colliders, and I want you to try and guess which columns they are. But when we checked our assumptions, everything actually looked pretty good. Surprisingly good, except for the correlation. So I don't think our results here are really all that off. However, one more however, you might have noticed that our target variable, okay, whether or not a person has diabetes or has been diagnosed with diabetes, it only takes two values, all right, 0 and 1, which represent no or yes, or like no diabetes or yes diabetes. And there's a special kind of linear regression designed specifically for cases like this called logistic regression. And it works pretty much the same way as linear regression, but it can only predict numbers between 0 and 1. I'm not worrying about how the math is different. The math is slightly different, but it's not too much different, okay? The output of a logistic regression model can be interpreted as the probability that a person has been diagnosed with diabetes. And a lot of people really like that interpretation. So let's fit a logistic regression model and compare the results to the linear regression that we just did. So here, from statsmodels.discrete_model, I'm importing the logit function, capital L logit. So that's the new model. Instead of sm.ols, we're going to use logit here. So create the model. I named it logistic regression, and then fit it. Okay, and it doesn't fit, it fits a different way, right? So it's going to give you some information on how well it fit. But then it still has that result.summary table that we had before, and I think that we're seeing pretty similar results, okay? The constant was important, and the glucose, right? We found evidence that glucose has an effect on the probability of being diagnosed with diabetes. Again, we found that BMI has a statistically significant relationship with the probability of being diagnosed with diabetes, diabetes pedigree function as well, and the two age buckets. And the coefficients should mostly be in the same direction, except for the constant. And the reason for that, it goes into the math, don't worry too much. But basically, what we're interested in here is like glucose has a coefficient of 1.0, BMI has a coefficient of 0.64. These are both positive, so as they go up, your probability of being diagnosed with diabetes also goes up. But glucose is higher, has a higher coefficient. One is higher than 0.64. So that means glucose actually has a bigger effect on your probability of being diagnosed with diabetes than BMI does. So what this means is that, in theory, if you think about it, A relatively skinny person or a person with low BMI who eats like a lot of sugar could still get diabetes. Now, in general, if you only have zeros and ones, you want to use logistic regression instead of linear regression, but neither one of them is technically wrong. So even though we did regular linear regression up here, we found very similar results, and you could have done this and reported it, and that would have been fine. You just need to understand what your model is doing and what the coefficients actually mean. So logistic regression, think about it as directly affecting the probability of being diagnosed, like in a very specific way. All right, let's get into some prediction. Finally, we're going to predict some stuff, all right? This is what makes data science and machine learning so powerful, okay? Really good predictions. Now, linear regression is probably the worst model in terms of predictive power, but it still does remarkably well compared to like traditional qualitative decision making. And before we get to predicting, there's one more concept that we need to talk about, and that is the train-test split. We need to split our data set into two groups that we're calling the training set and the testing set. Now, why would we do that? When we use a machine learning model, we will be using it on data that we haven't seen before and where we don't actually know what the answer is. Since we don't know what the answer is, we can't tell how accurate our model is, but we can get an idea of how accurate the model is by using part of our data to test the model. And this testing data needs to be withheld from the model, because if the model sees the testing data, then it doesn't count as a test anymore. Okay, so luckily, scikit-learn makes splitting this data really easy. You do from sklearn.model_selection import train test split. Train _ test _ split. And here, I'm splitting it into training and testing sets. So I'll have xtrain, xtest, ytrain, and ytest. And I'm using the train test split function on x and y. And I'm using 20% of the data for testing. All right, and here I'm just printing off the different shapes to make sure that they're correct. So we ended up with 601 rows in the training set and 151 rows in the testing set. Now we're going to fit a model. And I'm going to use the logistic regression model. And I want you to note here that we're doing the same thing as before, but now we're only using the training data, whereas before we were using the whole thing. Okay, so we've got this logit function, and we're using it on y_train and x_train, and then we're fitting it there. Now to make a prediction, you're just going to use log_model. That's the one that was fit. Okay, log_model.predict, and we're predicting on the test set, x_test. And that's going to give us our y_prediction. Okay, y_pred. And look at these. There's like, what is this, 0.75, 0.444, and so on. Now that, it doesn't exactly look right, does it? Because our original data, the y-test, is all zeros and ones, and these are decimals in between. So before we can really see how well the model predicts whether a person is diagnosed with diabetes, we need to sort these values into ones and zeros. And to do that, we're going to set a threshold where if the prediction is higher than the threshold, we can say it's a 1. And if it is below the threshold, we say it's a 0. And we can set any threshold we want. And picking the right threshold is an important skill. For now, though, we're just going to use 0.5. That's usually where most people start. It's just choose 0.5 and see what happens. So if the prediction is greater than the threshold, which is 0.5, then we're going to call it a 1. And if it's less than the threshold, we're going to call it a 0. So this is our new prediction. 1, 0, 0, 0, 1, and so on. Now let's talk about metrics. So metrics is how you evaluate how accurate your model is. So we're doing, this is called a classification. Okay, classification model, because we have ones and zeros, it's a binary outcome. We're not predicting a number, we're predicting whether or not a person has been diagnosed with diabetes. So we're going to use a different set of metrics than we would if we were doing like a standard regression and predicting a number. So here, there are a few metrics we're going to be interested in. The most obvious one is accuracy. The model's accuracy is how many of the predictions are correct. It's a super easy calculation in Python, but there's also a scikit-learn implementation. So if you just want to do it yourself, you say y_final is double equal to y_test, and then get the mean of that. which our model accuracy was 0.77, or it's right 77% of the time, all right? Now one of the tricks, though, because that sounds really high, but one of the tricky things is that sometimes your model can get a really high accuracy by just predicting the same value every time. So we want to check and make sure that's not happening, all right? And we're going to do that by looking at the value counts. So we see that our model predicted that a person did not have diabetes 107 times, and it predicted that a person does have diabetes 44 times. And that's really close to what's actually in the test set, where there are 103 people that have not been diagnosed with diabetes and 48 people that have been diagnosed. And those are similar numbers, and that's very encouraging. So it looks like our model is legitimately getting 77% of predictions correct. And here's the same thing using scikit-learn. So it's from sklearn.metrics, import accuracy underscore score, and then accuracy score of yfinal and ytest yields 0.7748, which is what we had before. I just rounded it. Another metric that we might be interested in is called precision. Now, precision answers the question, how many of the predicted positives are true? So in our case, that's how many of the people that we predicted have diabetes have actually been diagnosed with diabetes. Precision is a good metric when there are big drawbacks to predicting the positive and getting it wrong. Like, for example, say you're predicting which leads to target in a sales campaign. Now in that case, guessing that someone is a good lead and being wrong wastes the salesperson's time, and we don't want that. So in that case, you might want to aim for higher precision. Now, scikit-learn makes it easy to calculate precision. From sklearn.metrics, you import precision score, and then precision underscore score of y underscore final and y underscore test shows that our model right now, with the threshold at 0.5, has about 60% precision. Or 60% of the people that we predict have diabetes actually have diabetes. Now, recall answers a different question. It is, how many of the true positives are we catching? So in that case, it means how many of the people with diabetes are identified by our model. Now, this is a good metric when missing true values is a big problem, true positives. So for example, predicting whether a person has cancer, right? In that scenario, you want to catch every person who has cancer, because if you don't catch them, they will die, right? So you want to improve recall to do that. And scikit-learn makes it really easy to calculate recall as well. You do from sklearn.metrics, import recall underscore score. And then calculating it, you do recall score of yfinal and ytest. See that our model right now has about 0.66 or 66% recall, meaning that we accurately identify 66% of people that have been diagnosed with diabetes. Next thing we're going to look at is a confusion matrix. Now this is going to let you see where your errors are happening, and it can be useful for identifying problems with the model, such as biasness or imbalance between groups. So let's look at one, and then we'll talk about how to read it. Here we're importing from sklearn.metrics, import confusion underscore matrix and confusion matrix display. So first we calculate the confusion matrix by using confusion matrix of yfinal and ytest, and now we're going to display it, and then disp.plot here makes this, and it looks real nice. So this confusion matrix tells us that we accurately identified 88 people who do not have diabetes, and we accurately identified 29 people who have been diagnosed with diabetes, and we incorrectly predicted that 19 people who do not have diabetes do have diabetes. Okay, we said that these 19 people have diabetes, but they don't. And we inaccurately predicted that 15 people who have diabetes do not, meaning these 15 people, we predicted that they do not have diabetes, but they have been diagnosed with diabetes. So what I really look for in these is that the boxes on the diagonals have higher numbers than the boxes off the diagonals, so that's true here. And we also want to know that the boxes that are off the diagonals, okay, these errors, we want them to be pretty evenly distributed. So 15 and 19, that's evenly distributed. Both of these things that we want are true here, so it looks like this model is actually fitting really well. Lastly, a classification report. That's from sklearn.metrics, import classification underscore report. That just gives you a lot of information all at once. We can see the precision here at 0.6, the recall at 0.66. F1 score is like if you can't decide whether precision or recall are more important, then an F1 score is kind of a combination of the two. And these other things mean stuff, but don't worry about them too much right now. Just know that you can see a lot of the numbers all at the same time using your classification report. And in general, all of these three columns, precision, recall, and F1 score, higher is better. And that's enough. The last thing we're going to do today is we're going to choose the best threshold for accuracy. So up to this point, we've just used 0.5. Okay, but we can pick any number between 0 and 1 that we want. We just picked 0.5 because it's in the middle. So here we're going to check, and we're going to see what is the actual best threshold to get the most accurate model that we can. Okay, so I've just created an array of potential thresholds from 0.01 all the way to 0.99. It just goes up by 0.01, right? So 1%, 2%, whatever. And here I'm going to set up a loop. So I've set best threshold equals 0, best accuracy equals 0, best y is just the predictions, not even the binarized predictions, but just the regular predictions. And then I'm storing a list of accuracies here. So what this loop does is it goes through this array, all right, and for each number, I'm getting a new binarized y. So this y temp is like if the prediction is less than 0.01, then that's going to leave a 0. If it's higher than 0.01, it's going to leave a 1, and so on. It's going to loop through all of these. And then I'm getting the accuracy score between this binarized y underscore temp and the true values y underscore test. And if our temporary accuracy here is better than our best accuracy, which right now is 0, then we want the new best accuracy to be the temporary accuracy. We want our best threshold to be whatever threshold we just used. And we want our best predictions, best underscore y, to be equal to our temporary y. Then we're going to append the accuracies onto that list. So when you run this, it takes barely a second. It loops through all of these, does all the calculations, and it tells us that the best threshold is not 0.5, it's 0.71. And the best accuracy is actually 0.8146, which is a lot better than 0.77. Now here's our confusion matrix. So here we've accurately identified 102 people who do not have diabetes, accurately identified 21 that do. But we're predicting a lot of people have diabetes when they really don't. And that could be a problem. Depending on what you really want from your model, this could be a problem. However, I doubt it, because it would be better to say, oh man, you have diabetes, and be wrong, than to say, no, you don't have diabetes, and be wrong, right? So if there are errors, personally, I want them to be in this box, and this is where most of our errors are. However, the fact that this number is bigger than this number, that is problematic to me. That means that there is a systemic bias in the model that we could probably address if we wanted. Now let's check the precision and recall in this most accurate model. So the precision has gone way down from 0.6 to 0.44, but the recall has gone way up from 0.66 to 0.95. And if you look at the classification report, you can see that as well. So really, by just picking a good threshold, all right, we have significantly improved accuracy and recall of the model, even though our precision is a bit lower. And you know what, right here, right in front of you guys, what I want to do is I want to look at the best accuracies. Where is that at? Here it is. The accuracies list. And I want to see what is actually the relationship between accuracy and threshold. Let's see if I can figure out how to plot those without looking like an idiot. What did I call it? I called it possible thresholds. And y will have the accuracies. Yeah, see here? So as the threshold goes up, we can make this look better. We'll use Seaborn. It'll look a little nicer. Alright, so as the threshold goes up, you can see that our accuracy also goes up, but it kind of starts to like peter out maybe and be like stop improving really pretty low. Like at 0.4, it doesn't really improve much. And then once you get up here to pretty high, maybe 0.85, the accuracy actually starts to go down again. And that's it. That's everything you need to know to use linear regression, either for hypothesis testing or for making predictions.
Phew. So there you guys go. So you just saw how to use a linear regression model for hypothesis testing, okay, for drawing inference. And you saw how important linear regression is. I mean, it gives us the ability to say things like, oh, it is, that we have found evidence that BMI does have a statistical effect on the probability of being diagnosed with diabetes. And there are very few other tools that we have that allow us to say things like that from data. There aren't really a lot of solid statistical methods for learning new information from data like this. So linear regression and hypothesis testing are super important. There are links below to learn more about hypothesis testing because it's just used so widely across science and academia, really. So it's a super important thing to know. And then you guys also use linear regression, specifically logistic regression in this case, to predict whether or not people have been diagnosed with diabetes. And the model was pretty accurate, right? And this logistic regression is considered one of the worst predictive models that there is. So you can imagine what we're going to get into next week when we start learning about much more powerful models like decision trees and random forests and support vector machines and all kinds of stuff we're going to talk about next week. So I want you to leave your questions down below, and I want you to go through the questions down below and just see if you have anything to add. You don't have to have all of the answers to be able to help somebody else learn. And that is what we're all here for. So if you did learn something from this video, please give me a thumbs up. And if you want to keep learning with me, go ahead and subscribe. I'll see you guys next week.